I come from automotive. All of you probably are from energy side, from gas and gas and oil sector. But recently I heard Prime Minister, our Honorable Prime Minister, he talked about AI. So in this session we are also going to talk about AI quite a lot. What I have gathered from these speakers in our pre-discussion. Um, so AI, as far as Prime Minister has talked about, he has talked about AI is not just artificial intelligence in Indian context. It is all inclusive. Let me then just say, since we are going to talk about machine learning, I will say ML has much love, so all inclusive, much love. This is going to be the theme of this session, and I hope our speakers will do justice around it. But let me add some more acronyms which we are going to discuss in this session. So we have AI, we have machine learning, ML, DL, deep learning, AGI, artificial general intelligence, and of course Gen AI, generative artificial intelligence. Some studies have talked about what is going to be the future of artificial intelligence. So there is some number which I will throw in this August gathering, that AI will deliver around 15 trillion US dollars in terms of solutions by next year. And India as an economy, Bharat as an economy is going to be 5 trillion by next year. So you can, you know, this is massive, right, in terms of how AI will transform the world around us, and this is happening as we speak. So what essentially these acronyms mean for me per se is that there's a huge lot of story which is uncovering, which is to be told, and with that I will invite my first speaker, Mr. Alok Kumar Jha, to come on stage and talk about his presentation. Thank you. Over to you, Mr. Alok.
Good afternoon, everyone. I am Alok Kumar Jha from GAIL India Limited. I am working as a senior manager in National Gas Management Center of GAIL. It's one of its kind of center in India for managing the operations of entire national gas grid of GAIL. So if you all know that without GAIL, you cannot imagine the network of pipeline of gas, especially in India, because we are the, I'm not saying in a very gigantic manner that we are the leader in natural gas network in India. So starting our thinking in that direction, so earlier we are having lots of data in terms of direct data available from, you can say, pipeline by having applications like SCADA, CAPS. But that application and that approach is, you can say, more of kind of, it's a first principle technology. First principle of application, it means you are using the data and you are processing by your own experience and using some mathematical models. But in current scenario, without having applications like big data analytics, machine learning, you cannot go forward. So in this presentation, I will explain about that how GAIL has using these technologies to leverage its resources and using its, you can say, powerful data to make it more powerful, so that the customer at the end and the suppliers get benefited from that. So in left side, you can see that national gas grid of India, and in you are well aware that most of the network and most of the pipeline are being laid and supplied by GAIL only. GAIL holds around 70% of market share in natural gas transmission, and having more than 50% in gas trading segment. So being a leader, you should be more responsible, you should be more active towards keeping your customers happy, and more, you can say, rather than happy, you have to more responsive to your customers. And it's our utmost priority for GAIL. So talking about the simple natural gas drivers, you can say that in a current scenario, everyone needs an energy. And we are having in the India Energy Week, we discussed that the energy consumption of countries person is going to increase in a manifold manner in near 20-30 years. So presently we are in the scenario where oil and coal is a major source of supply energy, and we are also using as a transition fuel as a natural gas. But definitely we are having scope for a future energy, which is called as a biofuel, renewables, and any other things. But these things will take time to grow, because it having some advantages, but having some cost involved in it. And with the current scenario, the affordability of Indian people, it is not easy to cope up. So what are the challenges for natural gas industry? Apart from having, as I am a person from operations in gas in GAIL, so we are having multiple challenges apart from having the hydraulics management. Hydraulics management, I think I need to explain that it's a management to maintain the supply side and the customer, to make the supply side at such a level that the customer located at the farthest end cannot be suffered. Apart from these hydraulics challenges, we are having a challenges like marketing scenario. In the recent, you have seen the disturbances across globe because of some international relationship. Then, other than that, every energy segment is facing challenges from its internal sources as well as from external factors, that like some of the energy sources want to deassociate, or you can say replace other kind of source of energy. So in a natural gas industry, as an operation, we are having a biggest challenge to maintain the demand supply at such a level that the customer and supplier do not get affected. So apart from having these challenges, how we can categorize these challenges? The major challenges is the external factors. Definitely we are having the internal challenges that we can address upon by having our capabilities, by having our applications in our hand. By external factors, you need some of its kind of technologies, some of its supports from, you can say, new recent advancement in the terms of energy sectors. So you can see here the external factors that are more critical, that is marketing and international relationship, because it affects, because you can say in India, 50% or more than that energy requirement is being met from the international borders. So international relations plays a vital role in our natural gas system. Apart from that, LNG being a more competitive route right now in the world, everyone wants to play with the market of LNG because it's having a some added advantage for the companies. Apart from it, it comes under a regulatory environment, and the regulatory environments are changing very drastically over a period of time. So customer and supplier is well aware of that facts. So after coming into the factors, that the which are the disturbance or factors are more more, you can say, effective, or more how we can address that problems. So you can in the diagram you can see there are two types of disturbance I have categorized. One is called deterministic disturbances, and other is thing probabilistic. Deterministic kind of thing, seasonal variations, holidays, because you know in the holidays and the seasonal variations, some of the power plants, some of the city gas companies stops taking gas. So it gives the huge variation in the pipeline network. So for taking care of these disturbances, we need some intelligence in our system. So after coming on all the factors that are responsible or which are impacting our natural gas system, we can categorize this system in the, you can say, 4 phases. The phase 1 that involves the basic data of the pipeline. What are that? That are pressure, flow, composition, because it impacts our overall pipeline hydraulics management. Then it is an instantaneous data, but we cannot take a decision on instantaneous data. We have to take a decision based on the data which available through a time series. So we have a lot of amount of data in the historical manner that needs to be there. Then by having these internal data, you have to involve some external factors like seasonal variations, like international relations that I have already talked. Then after incorporating all these 3 phases, we have to inculcate, we have to, you can say, take a methodology or take a solution that can integrate all these 3 phases in a single manner. That is called the advanced technologies that we have used in our application, that is called machine learning technology. So it has played a very crucial role in addressing our problem in last several years that we have faced in GAIL. So as I have explained, we have taken a combined approach method, that is, you can say, phase 4. It has taken data directly from the transmitters, then process it, then taken a impact due to external factors. Then after taking all these impact, we have developed, you can say, a pattern recognition technology, a method of machine learning, and also uses the prediction of data based on the historical trends and how they are impacting to the system. So after having that, the machine learning, everyone knows, everyone wants to use in every segment, but how it can help in a natural gas pipeline network. So we have a data, instantaneous data directly from the system, that is from C-SCADA, C-apps, that is being used in GAIL over a period of time. We have a historical data, and we have a very long-term data for all the trends and available. We have more accurate data for, you can say, when you are having a data for a shorter time duration, you can predict only for a shorter duration. But you want to predict something that is for a longer duration. because everyone can predict that after 6 hours, 8 hours, or even 24 hours, what will be happen in your pipeline. But it is not easy for anyone to predict that what will happen after 72 hours, because any impact at the source in India, like you can say the gas sources are either in the coastal regions. So any impact on the source like Gujarat or in nowadays in eastern part in Odisha can impact the pipeline customers situated in UP, because it is a, you can say, transverse impact on the customer end. So after analyzing these all impacts and of analyzing all the, you can say, variation at the source and the customer side, we have developed a model based on inventory, whatever the inventory available in our pipeline network, and how it can be changed over a period of time due to any disturbance happened at source. So you can see the data is having with us. So how we can handle funds, in the left hand side, you can say we are having a list reports, we are having a graphical data, we are having some of the summaries of data that we have already developed over a period of time in either format, either in Excel, even some reports in the Word format also. Then we have to, you can say, data modeling process. So by using our database, either in Oracle and in Excel files, we have compiled all these data. Then we have managed all these data and made a relationship between these data. And then after making these relationship, we have analyzed the data. So for doing this application, we have taken a, you can say, software application especially designed for GAIL by SAS, and they have developed this application for GAIL so that we can having all these 4 parts of data to manage the, you can say, overall data handling concept of GAIL. Then we are having what modeling approach that we have adopted for making the application useful for our GAIL. That first we have developed a time series analysis of the data. Then by using statistical analysis and regression models, we have made our data nodes, that which nodes are more critical for our disturbances and how we can address that. Then we have to identify the lags. Lags means for any source that is situated at 600 kilometers away from the consumption. So how much time it takes to travel the disturbance from source to customer end. So that lag we have to identify. Then we have to do the, you can say, data aggregation. And by using that data aggregation, we have developed a model. So here you can see we have used these 2 models in our system. So one is mainly a hydraulics model, and then another is a scenario analysis. So this model is having a capability to make it happen on the real-time basis, as well as to you give the prediction that how much after, if you have any scenario that you are going to know that my one major customer situated in the north of part of India, and it will take a shutdown for a longer period of 30 days. So it will impact your entire pipeline hydraulics. So how you can manage your source side by taking a decision suitably in well advance. So these kind of trending available in our system, and it is real time as well as you can develop a simulation also. So we have shown is some graph. The red line shows that what are the prediction done by our model, and the blue line is showing that how we have done in over this period of time. So you can see that there is not such much variation in the red and blue line, and if any variation happens, then definitely you have to identify that why these are the variation happening between the red and blue lines for taking a corrected decision, so that in the next time when your model get predicted anything, that there should not be more difference between the prediction and the actual data. So right now, this last live we are sitting here in Goa. So we have taken example. Our GAIL pipeline is passing through Goa also. So we are having one biggest customer, that is Juari Goa earlier. Now it is known as Pradeep Phosphate Limited, PPL Goa. So here you can see in the box that I have shown that simulated scenario is showing what exactly happened in the prediction. So predicted volume and the actual volume. Based on that data, we have identified that if any customer is going to take a shutdown and their consumption is going to change from 0.5 million, how our pipeline hydraulics is going to change for a next 36 hours. This is another model that we have used by machine learning technology, that how our gas reconciliation, it is just a pictorial, it's not actual data. We have modulated this data for the purpose of presentation here. So you can see here that whatever the inventory we are having, how much gas we have purchased for the day and how much gas we have sold, and based on that reconciliation, we can predict, identify that where is the difference and why we are losing or having a negative, you can say loss of the gas in the network. So it's not been easy for us to, because in our public sector unit, it's not been easy to, you can say, take all the stakeholders on board, and how you can, because if the data is being used by another department, we are as from operations. So how we have to manage these challenges in the last 6 months of this project. So we have identified the tags, and we have identified which tags are having the sufficient historical data to make it a better analysis. Then how we can transfer the data from one system to another system. So it's a very huge amount of data, because you know GAIL is having around 17,000 kilometer of pipeline, and every pipeline is having every 20 kilometers we are having installation, and every installation is having more than 25 to 30 digital devices. So having these amount of data is not as easy for any system to handle. So we have implemented one OPC tunneler for taking out the data from our SCADA server to our model, so that the better, you can say, better insight can be given on the real time basis. Otherwise our system get hanged because of huge amount of data processing. So just one success story I can share with you. In the recent past, our major supplier in the Gujarat has got disturbed for around 36 hours, and there was sudden, because of cyclone happened in Gujarat. So by using this model, we are able to predict that which customer needs to cut down their supply at how much level, so that we can maintain at least optimum supply at all customer point. Earlier we used to do this by our only with the help of manual calculation, but after having this application, we are able to tell in advance that you are going to take this amount of cut in your supply by next 24 hours, because we are having a shortage at upstream. Earlier what we have to do, we have to do immediate cut to the customer, because we don't know how much it will time take to travel the disturbance from source to supply consumption point. Then apart from having this, you can say, more hydraulics management kind of thing, we have got benefit from reducing our energy consumption in compressors and other things over a period of time. So last the thing. Thank you from my side. Thank you.
Thank you, Alok, for your presentation. I missed to say that we will take the questions in the end. So we will run past all the presentation once, and then we will open up for discussions. So without further delay, I will invite Ajitabh Kumar. He is founder of Visage Technology, is a startup. So over to you, Ajitabh.
Good afternoon, everybody. I'm Ajitabh Kumar from Visage Technology. The title of my presentation is Long-Term Multivariate Production Forecasting using Transformer. So this is the outline of the presentation. First, I'll give the scope and objective of this study, which is to develop an AI-based surrogate for oil field production forecasting. Then I'll talk about the Olympus benchmark model, which is used in this study for validation purposes. Recently, AI-based surrogate models have been used for time series forecasting, and Transformer has come out as a state-of-art algorithm. So I'll talk about Transformer and its application in time series modeling. Then I'll talk about non-stationary transformer, because in oil field data, the things are changing very quickly. Our system is dynamic, so algorithm needs to learn the non-stationarity in the data. I'll show the modeling details and then some results. Finally, I'll conclude the presentation. So as I mentioned earlier, the goal of this study is to develop an AI-based surrogate for long-term multivariate oil field production forecasting. And in particular, we are interested in multi-phase flow supported by water injection. We want to handle an ensemble of realization, that is multiple simulation models, so as to capture the uncertainty in the production. And then we want to learn the inherent non-stationarity in the data, which is across the time horizon. For this, we have used non-stationary transformer. We'll show the application on the Olympus benchmark, and we'll also compare it with vanilla or the regular transformer-based surrogate and show how results improve. Okay, so let's first look at the Olympus benchmark model. It is a synthetic simulation model, and it is based on North Sea based oil field reservoirs. And it is 9 kilometer by 3 kilometer by 50. It has around 340,000 simulation grids, out of which around 190,000 are active. It has 5 phases, 1 boundary fault. What we are interested in is 11 production wells and 7 injection wells, and forecasted for that. And we have a simulation history of 20 years. To capture uncertainty, 50 realizations are there, but in this study we will use 10 of those. So we want to basically use our AI-based surrogate to forecast the production from the 11 production wells and 7 injection wells. In particular, we want to forecast 3 different variables for the production wells: oil and water production rate, and for the injection wells, water injection rate. So what is non-stationarity in time series? So basically, when we have our AI model, the basic assumption is that the statistical properties of the data set remains same or constant. It does not change with time or with place. But this is not true with a dynamic system. As soon as we start production from an oil field, the properties of reservoirs start changing. And statistical properties, may it be the relative permeability, the saturations, all of those start to change. So we need to capture this non-stationarity. So on the left, I'm showing one stationary data set where we have some mean and some fluctuation around that mean. So what can be non-stationarity if there is a trend in mean? So let's say our oil rate is going down with time, or water rate is going up with time. There's a step change. So there's a water cut happening and there's a sudden change in oil rate, or there's a change in variance with time. So recently, Transformer has been quite successful for time series modeling, and it is a state-of-art sequence-to-sequence model. And it is basically a stack of encoders and decoders, and uses self-attention in encoder to learn the feature, and then cross-attention in decoder to make the prediction. So the reason it is popular is because of its long-range dependency. So it is able to look throughout the history, and so we call it a global range modeling capability. And it has performed quite better than RNNs or something like LSTM. It is quite universal and flexible architecture. So there's few assumptions about structure of data. So it can be used across many different use cases. So I'm showing here the architecture of a basic transformer. On the left, we have encoder. On the right, we have decoder. And the key equation is the attention. Attention is basically how any data point is related to the historical events. And Q is the query. And K and V are keys and values. So basically, it uses this algorithm in the basic regular transformer architecture to calculate the relationships. So coming to our non-stationary oil field data case, here we need to capture how things are changing with time and how overall properties are changing once we start injecting water and producing oil. So the two key ideas are series stationarization and destationary attention. So in series stationarization, we say that we want to basically, for all the different chunks of time series data, we want to unify the statistics so that whatever we have learned in past can be used for future. And the first line basically shows that we are using mean and variance to unify the statistics. And then what happens is that because of this, our prediction capability increases. But another issue is that we lose some of the finer details which are in those temporal dependencies. And so then we use destationary attention, which is basically an ML-based approach. Here we have tau and sigma, which are also included in the AI model. And we update our attention equation so as to learn the destationary attention and capture those final details. So this is the problem that we are trying to solve. So for the single realization case, we are taking a single simulation model, and we have 29 different time series. And we have 11 production wells. For each of those wells, we have oil and water production rate. And for 7 injection wells, we have injection rate. And we have monthly data for 20-year production history. Then once we have validated our architecture for single case, we move on to the ensemble case, where we are using 10 different simulation models to capture the uncertainty and see whether the AI-based surrogate can actually handle such a large set of 290 time series simultaneously. So the architecture we have used, that we have 2 blocks for encoder and decoder. We have 512 convolutional and 2048 fully connected dimensions, 8 heads in multi-attention. And for learning the non-stationarity, we have de-stationary projectors with 4 layers and 32 dimensions. So getting away from details now and into the results. So on the left, I'm showing the results from state-of-art vanilla or regular transformer. On the right, I'm showing using the non-stationary transformer. The true value is shown in blue, and the red is the predicted value. We are giving model the historical data for the last 4 months, and we want it to predict for next 4 months. The vertical dashed line is where the training ends and validation and testing starts. So as you can see that even vanilla transformer is able to learn the historical data and performs okay for the training set that is left of the vertical dashed line. But as soon as we want to use this model for validation and testing, we can see that it shows a flat prediction. And this is because it is assuming that our data set is stationary. It does not learn the trend in the data set. Then, but if we look at the results from non-stationary transformer, we can see that it is able to learn the trend and all the variations and non-stationarity that is there in the data set. And it is performing equally good in training as well as test cases. This is for water production rate. Again, the similar thing. We can see that vanilla transformer is giving a flat prediction, which is not good enough, while non-stationary transformer is basically able to predict. Same is for water injection rate. Next, if we look into ensemble case, this is a quite complex problem because we need to model 290 different time series simultaneously using just one AI model. And the reason we want to use one AI model is that so that our predictions are unified. So as you can see that it is able to do quite well for both training as well as validation and testing part, and it gives quite a good match. We have used mean squared error or MSE loss for training. And if we look into the MSE values for vanilla transformer, it's good enough for training part, but as soon as we move into validation and test part, the errors rise sharply. And this is one of the key things that we want to convey, that oil field data is not stationary, and so regular or generic AI algorithm may not be able to capture the dynamic system. Then when we use non-stationary transformer, we can see that there's only slight increase in MSE value even for validation and test case because it is able to learn the non-stationarity and trend in the data. So with this, I will conclude the presentation. We have used non-stationary transformer-based surrogate model for oil field production forecasting. It is able to capture the underlying dynamical system and the non-stationarity in the data set. It has 2 key modules, series stationarization and de-stationary attention, and it outperforms the state-of-the-art vanilla transformer-based surrogate. With this, I would like to thank cloud computing provider OVH for cloud credits and TNO for providing us with Olympus benchmark model. And please feel free to contact with us for any future questions. Thank you.
Thank you, Ajitabh. Thank you for closing in well before time. So, but we will stay back for the questions. So let me just invite the next speaker, Sreenath S. He is from ONGC, Executive Engineer. Over to you, Sreenath.
Good afternoon, everyone. So I am Sreenath S. I'm an executive engineer from Oil and Natural Gas Corporation. And it's with great honor that I stand before you today to discuss the application of AI in solving one of the crucial aspect of drilling operation, that is the kick detection. So the studies for the kick detection is not new. It has been around for several decades as of now. But this paper is unique in two aspects, two key aspects. The first one is this paper is written from a very practical perspective. So it takes into consideration all the data inconsistencies that happens to a real-time data set. And the second aspect is instead of using the drilling parameters as such, this paper is introducing a new derived variable and use that for the analysis of kick detection. So as many of the upstream experts already know, the kick event is often defined as the unexpected or unanticipated flow of hydrocarbons into the wellbore. So it is not just the reservoir that can push hydrocarbons into the well. So during drilling, we can encounter any gas pockets. It can happen anywhere within the depth, and that can push hydrocarbons into this wellbore, right? So what is the control mechanism for this? Because these hydrocarbons are under a lot of pressure on its own due to the high stress of the rock beds, because we are talking about the depths of thousands of meters. So they don't need any external factor to come up to the surface. So there is a pressure that is pushing these hydrocarbons to the surface, right? So the control mechanism is you put pressure from the surface into the wellbore. We do this using a drilling fluid. So normally we use a water-based mud as a drilling fluid and exerts the hydrostatic pressure of the mud into the reservoir, which can counterbalance the pressure which is exerted from the pore, right? So in this aspect, the density of the mud has to be very carefully chosen so that it rightly balances the pressure from the pore. So if the drilling engineer is not able to do that, that can lead to the event called the kick. And if not controlled in time, that can lead to a very catastrophic event, which is known as the blowout. So this blowout can lead to financial loss, risk to human life, environmental damages, and whatnot. So because of this, because of the relevance of kick detection, so there were a lot of studies throughout these years, and the studies actually date back to the 1980s, where we have a lot of rule-based models or threshold models. Basically works with a cutoff, very simple models. And we have a physics-based model where the parameters of the kick is represented by a physical equation. Then came up different statistical and probabilistic models where we assign a risk score to each of the risk elements in the kick, and final probability is calculated using a Bayesian network or similar tech. But with the advent of AI, with the emergence of AI in the 2010s, we have a lot of studies which uses machine learning to solve the issue of kick detection. So we can see that these are some of the notable studies ranging from the 2014s and up to 2020. These are very notable studies that uses a wide range of machine learning models like ANNs, SVMs. We have Bayesian networks, we have pattern recognition and everything. But one key factor is similar to all these studies, that is their data set is way too perfect, which is not from a practical perspective. You don't find that kind of a data set anywhere in our real life. So they have a very perfect balanced data set of 50% kick and 50% of normal drilling data, and they've done the analysis on top of that. So the actual distribution of data is it's similar to this graph that is shown here. So the data set that I've chosen, it has 99.99 data of normal drilling, and the rest, only 0.01% of the data is representing the kick. So these kind of data imbalance or data parity is there in the real scenario. So just a summary on different models. We have simple models like linear decision trees and pattern recognition models. Even though they are very explainable models, they are way too simple to generalize complex linear relationship between the variables. We have artificial neural networks, which is state of the art. It can get the work done. It is adopted by different industries. But for kick detection specifically, we need to see the trend of the last 60 seconds or 120 seconds. So there is a time factor which is also come into picture, which artificial neural networks are very inefficient in. So we have ANN plus time is RNN, which is the recurrent neural network. And LSTM is considered to be the most sophisticated models currently in the time series domain. So even though this is the LSTM based RNN models are adopted by the healthcare sector and the finance sector for time series analysis, this does not fit for kick detection because of the data parity that I've discussed in the previous slide. Because we are dealing with the data parity of 99.99 and 0.01 here. So even the LSTM RNN is not a good fit for our use case. So what is the problem statement in hand right now? So we have to design a model that can handle the data disparity, the data inconsistency, or in the data science term, we call it class imbalance. It should be able to handle the time series nature of the dataset. It should be explainable because we know artificial neural networks are black box model, and there is no real explainability for as of why AI had made that decision. So our model has to be explainable as well as it should be fast and reliable and scalable as well. So let me just break down the problem statement into three different parts. The first one is regarding the data imbalance. So rather than training a conventional multi-class classification or a regression model, we are going to train an anomaly detector using autoencoders, so that we have to pass in only the normal drilling data for training this model, and there we need less or no kick data to train this anomaly detector. So that takes care of the data imbalance part. Second thing, LSTM, the LSTM RNN based model will be the building block of our autoencoder. So that will take care of the time series part. Now, for the explainable part, we are borrowing a lot of physics concept from the drilling physics, so that it will be explainable. That will come in the later slides as well, by how it becomes explainable. So this is the data set selection. So the data used for training the model has been taken from 3 different drilling rigs. It is almost 3 months of data. So we had to do a lot of EDA to get it cleaned. As we know, the data from the field, directly from the field, is very noisy. So we have to apply a lot of outliner removal and relevancy analysis for this. In addition to this, to pass into an LSTM model, we need to do some temporalization on top of it. We need to do some additional pre-processing like batch normalization and stuff like that. And once that is done, this is the heart of our model, which is an LSTM autoencoder. So in simple terms, what is an autoencoder? So there is 2 parts as represented here. It has an encoder and a decoder, right? So the main aim of the LSTM encoder is to learn all the possible patterns that can happen in a normal drilling operation. So it learns the patterns of the normal drilling operation, and whenever an anomaly comes, it flags it as a kick. So that we don't need any kick data for training this model, which is what actually the real life representation of the data looks like. Now, even after training this model, let me just go back to the slide. So this is a very sophisticated model. So I was expecting a very impressive results from this. But the results were mediocre. It was just above average. I was getting an accuracy of something around 70, and the F1 score was something around 80, which I was not expecting. So I am doing something very terrible. I'm missing some part of this. That had me checking. I had to go through all the logs and found something very critical. So actually, when I checked the logs, I can see that the model were confused as what an anomaly is. So you can see that this is a graph between the motor's SPM, the strokes per minute, and the standpipe pressure. So the standpipe pressure is actually a very reliable metric of detecting whether the event is a kick or not. But you can see that it is fluctuating like anything. And the model is confusing this as anomaly. But actually what the anomaly is, you can see the part where the white color is, so the green part is actually the normal drilling, and you can see when the orange curve is going down, you can see that the blue curve is going up. So the actual anomaly is how the 2 variables behave with each other rather than the sudden fluctuation of the data. So we have to redefine what actually an anomaly is. So what we have to actually do is to couple some variables. So I have to get advice from drilling experts, And these are the correlations that I have devised. So the SPP average and total SPM, they have a very positive correlation during normal operation, but during kick, it suddenly changed into negative. So we have to pass this correlation parameters as the input, but instead of using the actual drilling parameters as such. So this is the novelty in the paper. So we can see that in the first slide, in the first figure, you can see that the orange and the blue have a slight negative correlation, which is an anomaly. Whereas in the first, in the second image, both are perfectly correlation that represents a very normal drilling. So the key takeaways of this paper is the LSTM autoencoders found much better than the LSTM RNNs. Since we are dealing with a lot of noise, we had to use a filter function for this. The medium filter has found more performant than the other noise reduction functions. And we have found 4 new derived correlation. So that is represented in the table for analysis instead of all the drilling parameters which is being used. So the novel segmented correlation function is found to be more performant than the normal conventional drilling analysis. And this was the initial results where I was not using the correlation function. The F1 score was okay, it was good, but not perfect. But with the segmented correlation function, the F1 score of the confusion, you can see the confusion metrics, that F1 score was something around 99%. So this is the final results of the model. And the way forward, so we have to gather data sets from a wide variety of geological profile. So we need to also include the geotechnical order where it represents what type of rock is present at what depth. And we have to extend this study to various other complications like mudflows and stuck pipes and stuff like that. And instead of using an LSTM, we are also exploring the attention architecture that was said by the previous speaker. So we are also planning to use a transformer-like architecture instead of LSTM. So this is the way forward. Thank you, sir.
Srinath, looks like hybrid solution is the way forward looking at AI solutions, where we stand today in terms of data which is coming up. May I invite the next speaker, the last speaker for today's session 20, Ritesh Lal Shaw from Indian Oil Corporation. Over to you, Ritesh.
Good afternoon, everyone. I am Ritesh Lal Shaw, an officer of Indian Oil Corporation. Today, I will present on the topic of missing log imputation using machine learning. So, here the word missing log. It means that absence of some data from oil logging tools. It may be porosity logs, it may be resistivity logs or any other logs. So, we can define our problem that why the missing log present. So, there is several reasons for that presence of missing log. At first is the drilling condition. High temperature and pressure cause the damages of measuring instrument. Second, instrumental fault. Third, absence of some logs in old oils and etc. So, presence of missing log, it's a serious concern for the GNG person to get the complete idea of the borehole data. So, in 1950s, there are Post, Kastanga, many scientists have provide some statistical and empirical model to predict some missing logs. But these models have some limitations. First is that this is the specific for the rock types. Second is it requires calibration time and required experience. So recently the most popular one is missing log prediction using machine learning. I will discuss on that. So each machine learning project has 7 stages. At first is the data gathering and pre-processing. Here we gather the data and pre-process the data. Second is exploratory data analysis. Here we find out the characteristics of the data of each variable and find the correlation between the data. Third is the feature engineering. Here we try to create a new feature. Say suppose we have some data of the house prediction, price of the house predictions, and we have the data of the number of rooms, number of kitchens, number of bathrooms. So in that step, we can create a new feature, that is the area, which is more relevant to predict the house of the price of the house. So fourth is the model selections and training. Different algorithms are used for the model selections and the performance are compared to get the final models. Then we can improve the final model by hyperparameter tuning. Last is the model deployment and apply some testings. So this is the workflow of my study. At first, we just import the data, and here we use the two-way log data. One is for the training and one for the testing purpose. Here, each log has 4 logs. First is the porosity logs or neutron logs. Second is the density log. Third is the resistivity log, and fourth is the gamma logs. So these all the data are trained for the model, and here the input 3 logs are used as an input and 1 log is used as a output. So after the training, we test the model using the testing data. So here we used 2 models. At first is the extreme gradient boosting or XG boost. Second is the random forest. Now what is the random forest? So random forest is a basically bagging based method. It combination of the 2 words. At first is the random, second is the forest. Forest signifies the collection of some trees. Here trees mean the decision trees. Each decision tree is itself a flowchart like ML model. And random word comes from the bootstrapping method. Here all the data are selected randomly. So we can conclude that all the data are select randomly and give it to the one decision tree, and decision tree give us some output, and all outputs of each decision tree are aggregated to get our output of the random forest. In case of classification problem, majority votes are used for the as an output, and in case of regression problem, average is used in case of random forest. Now XGBoost. XGBoost is a bootstrapping algorithm. Here all the data are come to the first model. Then we calculate the residuals. Then these residuals are fitted with the another model or additional of models. So we can see that each steps. At first the base estimator, that is our first model. We have no data, so we can use that mean variable as our first model. Then we can calculate the residuals, and after that we train the models, and again it will be process will be iterate until the cutoff is reached. Here the cutoff will be the number of additional models or the accuracy of the residuals. So in my study area is in the northeast of India at Bhokpara Wellfield in Upper Assam region. So my target formation is the Tipam sandstone formation, and this formation generally 500 meter vary in our both wells, that is the training and the testing wells. The table shows the statistics of our 2 wells, that well 6 and well 8. So this is the well line logging response of our training well and testing well. Left one is shows the training well and right one is shows the testing well. Here we predict the neutron log or the blue color logs using the resistivity logs, density logs and the gamma rho logs. So the upper one shows the overlay of true and predicted response of random forest algorithm, and the lower one is for XGBoost. Here the base slope, here the points nearby the base slope fitted lines are the base fitted points, and the as we move towards the move away from the best fitted line, it shows the how poorly fitted the data. So this is the same in the depth domain. This is the overlay of the training, predicted response, and the true response. We can show that it is good correlate with our true data. So this shows the conclusions, and the table shows the RMSE, means root mean square error, and correlation coefficient for both algorithms. So from the table, we can conclude that the forest, random forest and XGBoost both performs well. And if we compare that the XGBoost performs much better than the random forest. And second is that machine learning techniques like that we can use to predict the missing logs. Third, as I said that this is the data driven model. As the number of datas are more, the more is the accurate of our model. So if we use more number of data, then more number of success or confidence will be more. So that's all. Thank you everyone.
Thank you, Ritesh. May I now request, with this we conclude all the presentation, but we have time. Please stay put. I'm requesting my fellow colleague, Mr. Pravin Shahu, to please take over. Thank you.
So I thanks all the delegates for attending this session and speakers. Thank you very much.